Hello Internet. In this video, we are going to try and create a tensor class from scratch. We are going to be creating a tensor class that behaves like tensor classes from other machine learning frameworks like Tinygrad and PyTorch. By doing this, we hope to learn the basics of this class. So let's start by creating a file called tensor.py. And here I'm going to create a class called tensor. It's going to have a constructor that takes a size as input. The size is going to be, say, 1. That's all we need for now. So let's assign the size to a property called size. And we are going to be creating the data for this tensor based on the size. And by default, we'll be using random values for the data. So let's import random. Here, we need to be using a for loop to initialize it with uniform values from -1 to +1. And here we'll say for underscore in range size. Okay. So yeah, we have a basic version of the tensor class. So let's say we pass 5 to this, and let's try to print the data. Okay, we got 5 random values, just as expected. But I don't want the user to be directly looking at the data attribute of our class. So let's update the representation of the tensor. So here we can return a nice string that describes our tensor. So I'm going to say tensor and then size equals size and data is solved. Now this should be self.size. This should be self.data. Okay, so now if I say print p, we should be looking at a better representation. Great. Now Tinygrad has a very similar representation for its own tensor class. So, but yeah, it's a lazy tensor, so there will be differences. But now let us update the constructor so that we can actually specify the data. So by default, it's going to be none. So if data is available, we're going to set the data to data. Only otherwise, we are going to be changing this here. It's probably a good idea to assert here to make sure that size matches the length of the data. Okay, so now I could say something like and things should still work. Okay, so this works. Good. So now it's time to add some operations to our tensor. Let's start with addition. So I'm gonna override the add method here, and this is gonna take 2 tensors. And it's gonna return a tensor whose size is equal to the size of self. We can add an assert here, so make sure that the size of self matches the size of a tensor that we are adding its width. So now I'm gonna say data equals we need to be making use of a for loop now, because unlike Tinygrad, we are working with lists directly, right? Tinygrad makes use of NumPy arrays, but we are working with lists. So I'm gonna make use of the zip function. And the zip, and we're gonna say self.data, tensor.data. So this will allow us to work with one item of each array of each list at a time. So let's see if this worked. Gonna solve this A and this B. Let's see if A plus B works. So we should be seeing a tensor that says 6, 8, and 10. 6, 8, and 10. Okay, so addition works. But now Tinygrad maintains a tree for doing the backward pass. So let's create a tree for our tensor as well. Now here I'm going to say tree. Its default value is going to be an empty list. And here we are just going to say self.tree equals tree. Nothing special here. But now here, when an addition operation happens, we need to update the tree. So here let's say this is a plus operation, and the first argument is self and the second argument is tensor. So very simple. So this will allow us to maintain a tree. I could say print the tree of this tensor. So you can see here that we have the plus operation, the first tensor, and the second tensor. Okay, so we are creating a tree. So let's create the multiply operation now. This is 1, 2, 3, 4, 5, 7. 7 y and e. We'll call this mul and replace this with the star symbol, and again star symbol here. let's create another tensor called C here. And here I'm going to say, I don't know, something simple like 3, 4, 2. So let's multiply this with C. So this will follow the rules of precedence. So first B and C will be multiplied, and then A will be added to the result. Let's see if that is correct. Okay, so we have a plus operation with 1, 2, 3, and the second operand here is 15, 24, and 14. We didn't create a tensor like that. So we are looking at the result of the multiplication operation. Is that right? 15, 24, and 14. Right? Yeah, 5 times 3 is 15, 24, and 14. Yeah, it makes sense. Okay, and working with something like star and plus doesn't look very good. Let's make use of an enum. So from here, import enum, and we are going to create something called ops. And here we are going to have our operations. So we'll call it add volt. And this we can replace with ops.mul. And this with ops.add. Okay, so you can see this looks much better. Now that we have a tree, let's try to display the tree. Tinygrad can, so we should be able to, isn't it? So we need to do a depth first search here. So let's create a function called dfs that accepts a tensor. And if the tree property of the tensor is none, okay, if not, tensor.tree would be ground. Let's just say print leaf node. Otherwise, we are going to print the operation. So this would be tensor.tree of 0. And then we recursively call the tensor with the left branch first, and then the right branch. Okay, so let's try to print. Let's try to assign a plus b star c to a new variable. And get the tree of that variable. I hope there are no errors here. Okay, we got something, but it doesn't really look like a tree because we are not really looking at the depths here. Let's create a depth argument here. By default, it's going to be 0. And based on the depth, we are going to print spaces. And we are not going to have a new line here. So with this, okay, so what went wrong? Okay, yeah, we need to update the depth. So we have to say depth plus 1 and depth plus 1. So great. So we can see that the multiplication operation happens here, and the result is added to the other leaf. We should multiply this with 2 to make the operation more apparent, to make the tree structure more apparent. This looks much better. Okay, let's add one more operation to our tensor, and we're going to call it a day. So this operation is slightly more involved than a simple addition and multiplication operation. So let's create a dot. Okay, to be able to use reduce, you need to import onc tools. And let's import operator as op. So here we return a tensor whose size is going to be 1, because the result of a dot product is always going to be a single value. But the data is going to be something called ACK, and the tree is going to be dot, and again self tells you. So now it's time to define ACK. So ACK is going to be a reduce operation where we are adding. So here we can simply say tensor star self star tensor dot data. Okay, so for this work, let's delete D, C. Let's try to calculate the dot product of A and B. I'm gonna say A dot B. So the output here will be 5 times 1 plus 6 times 2 plus 7 times 3. So 5 plus 12 plus 21. Let's see if we manage to get the right value. $947. An additional closing bracket. Okay. 38. Looks right. What were the values? So let's assert this. Assert D data equals 5 start 2 plus start 3. No errors, so that worked. Great, now you know how to create a tensor and add operators to it. In the next video, we'll try to do some gradient descent and create an optimizer for this, a stochastic gradient descent optimizer perhaps. Please like and subscribe if you like this kind of videos.